Okay, I think we are live now. Hello, everyone. Thank you so much for joining in on day three essentials for data analysis. Okay, and this will be our last day. And so, if you are here for the 3 consecutive days, so thank you so much for being here. And yeah, so let's start off with this session and let's put this on a good end. Let me share my screen with you guys first. Okay, I think it's visible now. Let's not. Hmm, yeah, now it's visible. All right, so let's start. So first, I would like to address the audience here, whoever we have here in the chat. Hello, Ratna, and hello. Okay, so okay, hello. All right, so where we exactly we were at was at a certain point, right? Like you understood what was your pair plot was all about, right? Like how exactly you can utilize the pair plot, and when you don't have three-dimensional data, or when you have more than three-dimensional data, well, in that case, you can definitely go with the pair plot. But there are some limitations though. What exactly your limitations are? So in pair plots it doesn't help much when we have huge number of dimensions. The very reason for that, if you like for example, let's say right now what the number of dimensions we tackled with this case study was 4, right? So we got around 16 plots from there. Okay, and let's say we have got 10 dimensions. Well, in that case, we will be having 10 C2, which will gonna equate to 45, and then we also gonna have 45 replicas, so it will gonna be 90. Okay, and we also gonna have 45 another those histograms as well, so it will be another 45 here, right? So it will gonna so not 45 though, not 45 though, sorry, not 45 though, but 90 plus 10. You will gonna have 10 features, so it will be 100 plots for 10 dimensions. Just for 10 dimensions it will just gonna explode till the 100. So it's not at all readable, you know like okay. So therefore we will not gonna go with the more than 4 or 5 or 6. Okay, so that is why I just made an observation here. Doesn't help much when we have a huge number of dimensions. All right, okay, now is the next part. So now let's actually, I guess we did talk about in brief manner what was your univariate analysis will be all about. So let's talk about this first here. So what you are seeing here is your histogram. What exactly your histogram is, let me first tell you. Okay, like what exactly it is. So histogram. So it basically shows you a distribution with a certain interval. You're right, a distribution with an interval having a frequency. Okay, so what do I mean by that? Let's say we have got this certain data set here. Okay, and in this data we have got, let's say, 0 to 10 as a first interval. Then we have here 10 to 20, another one. Then we have 20 to 30, 30 to 40, and 40 to 50. I'm just taking random guesses here, 0 to 50. And in this one we have got 45 data points. In this one we can have 57. In this one we can have, let's say, 61. Then and then we can have 38 and 12. Okay, and now if I want to plot this data onto a histogram, so how exactly I can do it? So you can just go with this one, like simple x and y plane here. Okay, and then you can basically segregate this entire x axis on these values. How exactly? First will be a 0. Sorry, it will be a 0 point, and then we will gonna have 10, 20, 30, 40, and 50. Right. So till 0 to 10, how many like this is the your frequency value, right? And this is your interval here. Okay. So when we talk about this, right, like it will be around like let's say 45, let's say around here. And then 10 to 20, we have 57, so it will be somewhat larger than this. Okay. And then we have 50, like 20 to 30, we have 61, so it will be also larger than this in the height, of course. And then we have 30 to 40, which is 38, so it will be lower than this, and it will be the lowest because it is only 12. Okay, so this data is a formation or like is a representation in the form of his histogram, like here, what you are seeing here. Okay, and now let's talk about some more details about the certain histogram. So like this certain, like breadth will be referred as like bin width. What exactly is your bin? So your bin contains like number of data points. Okay, how exactly? So let's see. So when we go with this one, so I would like to I would like you to show you something else here. Day one, got this day one notebook here. Good evening. Hello Aniket. Hello Nandini. Hello Mariam. Good evening to all of you. Good evening. Okay. Good evening. Very good evening. Okay. So like if we talk about this certain like histogram, so I think I have had here somewhere. Okay. Yeah. There you go. All right. So we do have it here. And let's talk about this one, right? So we cannot definitely go into the full-blown details of like how exactly the histogram is formed up, like in a way where we can actually represent the mathematical formulation. But I can definitely give you an intuitive, like understanding about how you can interpret this entire graph. So the very first thing which you are seeing here is like this is your like basic histogram, okay, and this data is like I just created with the help of NumPy. Like I'm creating this data with the 170 as a mean. This is my mean value, and this is my standard deviation, and this is number of data points. Okay, this is my number of data points. So how many values do you see here? Like we have got this heights, edge color, and like the bins. Okay, so how many numbers do you see here? Like 250 here. And what do I mean by the bins here though? Like bins I am taking as a 10. Okay, so I like we have got a formula for this, like the mathematical formula. So your bin can represent the number of data point a window will gonna have. So like if I say like let's say for this one, like let's say for this one, the formula for this one will be like the maximum height for this like the maximum height for this entire data frame or for this entire data set. Okay, which in this case I don't know what exactly it will be, but let's say like it actually is. Let me actually show you like what exactly it will be. Oh, okay. So like the maximum height will be around like for maybe like 200 something, like like this is what we have as a maximum. Okay, and divided by minimum height, whatever the minimum height we're gonna have, like it will be around like here. Okay, 145 or something like that. And then we will gonna multiply, sorry, then we will gonna just divide it, like this difference, sorry, minus, it will be a minus 200 minus 145 divided by the number of bins. So this will just gonna show you like how many data points this certain window can have. So if I go with this one, like let's say for this one, I've got like we have got here 5.3. So let's approximate this value to 5. Okay, when I do that, and if I go here, let's actually like closely observe this graph here. So like let's only talk about like let's say this one. Let's say for this one, how many data points you can actually calculate or you can actually see from here. It is around 150. So it can be like we can actually perceive like it will be 150, then it will be 152. Then we can see like it is ending somewhere around 160 here. So it will be approximately 158 or 155, sorry, 158 or 157, approximately this value. 152 to 157. Okay, so these many data points, like you have 5.3 data points here. So like approximately it will be 5. So this is what it shows. Okay, and of course, the more you will gonna, like let's say changing the bin size. Like let me actually just like show you. Or so here if you can see, like the maximum height I have got here is 192. Okay, I just take an example. So I have got here like 5.5 as my number of data points. Okay, so width of a single bin. Okay, this is what it is. So now if I go here, so again, like you can like I just took this example from this certain reference, so you can always like take a look at it. All right. So of course, so what you can notice here, the as you grow the number of bins, right? Like as you grow the number of bins, the width size will definitely gonna increase. So if I talk about, let's say, how many number of bins do you see here? Like in this case, it is by default 10. So it is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Right. And the moment you will gonna increase it, the number of like the number of width or the number of data points an interval can contain will gonna shrink, right? Okay. So this will just gonna shrink further because we are increasing the bin size here, right? Okay. So you can also see that like in action when I increase the bin size like from 10 to 15. Earlier it was able to contain 5.5. Now it is being able to contain only 3.6. So like the bin size actually matters for the width of a like certain interval. Okay, so that was your like you can see like okay, that was your histogram. Okay, and just the moment we understood the histogram, right? The smoothed version of it, I can just show you right away. Like here, we understood histogram. Okay, the smoothed version of a histogram is probability distribution function. What do I mean by that? So let's actually try to smooth it out. So if I try to smooth it out, I will just gonna I will just gonna consider the edges. Like what edges do I have here? Like this. Okay. And if I project this onto a different XY plane, let's say for this one, like I've got here, like smoothed version of it. How exactly I can see this? Like this. I know like I may be making some mistakes here, but this is the best I can do in terms of drawing on like some graphs because my drawing actually sucks. X and Y. So like this is your PDF function or sorry PDF in like plot probability density like sorry distribution function. Okay, but what exactly it is? Let's also talk about this like right away. So I can just show you here PDF function and let's see that in action on the like Wikipedia itself. Okay, so here. Okay, not here though. This is your PDF function, guys. Mm, there you go. Okay, this certain equation is your PDF function. How exactly it works? Let's see. So in this case, your sigma square is a variance. Variance is like what is the spread? Like variance is nothing but the measure of spread. Like like how much data you can spread across your x-axis or y-axis. That is the variance. Okay. And when we take a square root of your variance, it is your standard deviation. Okay, two terminologies are clear. Second, third, sorry, we have here is mu. So mu will be your mean. mean of all data points. Okay, all right. And like this 1 over under root 2 pi is nothing but a constant. And like this is the equation, the main equation we have. Okay, this equation represents a bell curve. But what do I mean by that, the bell curve? Okay, so we want to understand just in a while, like what exactly your PDF and CDFs are. Like probability density functions is cumulative distribution functions. Sorry, density functions. Like how exactly they relate to each other. That will gonna make much more sense just in a while. But even before that, like we cannot derive this equation from scratch for sure. But this equation basically produces a bell curve. And given that all of your data points, like your data points are normalized ones. Okay, what do I mean by that? Okay, what do I mean by that? So if I go back here and let's actually open this in a new tab, not the image though, but okay, this is much better. I hope so it is. Okay, this is much better now. So let's talk about this certain graph and equation and everything. Just for now, forget about this one. Like this is your box plot, which we will gonna study just in a while. But this is your like your bell curve. Like how exactly you can read this out loud, like in simple plain English. So which we saw, your bell curve was like fx of some mu1 sigma square, and we gave it like 1 over sigma root 2 pi, right? Like something like I don't really recall the equation. Okay, 2 root pi and sigma exp of like whatever the equation we had there. Okay, so whenever you start, like you can have x values. X values will be your features, right? Your features what? Like your features will be a set of what? Set of like independent variables, like sepal length, sepal width, petal length, and petal width are your independent variables. Okay, so therefore there those are your features. Okay, and now like the moment you will gonna put those like the data in this certain equation, you will gonna generate something similar, not exactly like this, but something similar. Okay, so what exactly this is all about, let's see. Okay, so like in this certain like in this certain region, and in this certain region you can actually take a lot of observations out of it. Okay, but how so? So your bell curve follows a rule called 68, 95, 99.1. Okay, so how exactly it is useful though? You might actually make an just a sec. You might ask me, right? Like how exactly it is useful. So for let's say if I talk about 68, in like 99. Okay, there you go. 99.7. Sorry, not 99.1, but 99.7. Let's talk about this so I can actually have a data set here. Okay, open image. There you go. Uh, okay, there you go. So we have got this certain data set here. Okay, let's talk about this one. Okay, so this is again your bell curve, which was represented by your normal, like that equation, PDF equation. Okay, and this region is consists of 68% of data, and this is your, and then when we also add this region and this is region, so this entire region becomes 95, and when we also add this and this actually becomes 99.7. But how exactly it is useful? You might, argue with me. So let's talk about let's suppose you have got like the data for heights. Okay, data for heights where mean height is 170 centimeter. Okay, and which varies with the 10 centimeter up and down. Okay, all right. So here it is your mu. This is your mu value here, and this is your first sigma. Like it will be a minus sigma plus sigma. This will be a minus 2 sigma. This will be your 2 sigma. Sorry, this will be a 3 sigma. This will be a minus 3 sigma. Okay, so if we talk about this certain region, like this 68% can be like, will gonna belong to mu minus sigma, mu plus sigma. Okay, and your 95% will gonna belong to mu minus 2 sigma and mu plus 2 sigma. And of course, your 99.7% will gonna belong to mu minus 3 sigma and mu plus 3 sigma. All right, that's great. So like, let's say we have got this mean value here this much and standard deviation this much. Okay, fair enough. And now let's say if I want to ask, like, 60% of my data, of height data, like falls between what? 170 minus sigma, which is 10, and 170 plus sigma, which is 10 again. So 60% of those heights actually fall between what? 160 centimeter to 180 centimeter. That that powerful this, like, observation is. Like, you have got like, this certain observation or this certain assessment just by having those mu and sigma values. And you also knew, like, this certain distribution or this certain data points, like, follows a Gaussian distribution. Yes, this is also known as a Gaussian distribution, or sometimes even normal, or sometimes even as PDF. Okay, like, we basically use like these terminologies interchangeably more often. All right. Okay. So that powerful it is. And when we talk about, like, this is only for the 68%. Okay. But what if I wanna calculate, like how much value it will be? Like, for this one, for this region. Just only focus upon this one. So it will be for mu plus 2 sigma and mu like plus 3 sigma. For this one, it will be mu plus 2 sigma, and this will be for mu plus 3 sigma. And this certain region only consists of 2.35% of data. Okay, so 2.35% of data belongs to what? Mu plus 2 sigma and mu plus 3 sigma. All right, so what we have here as mu is 170 and sigma is 10. So it will be 170 plus 2 sigma, which is like 20, and 170 plus 3 sigma, which in this case will be 30. So it will be 190 to 200. So it is basically, like, how exactly we can read this out loud? Like, only 2.35%, male height falls under this range. This is what it means. And also, like, it is also true for this one as well, but in a negative way, right? Right now, what we are basically taking as an extremity of how extreme this value can get, and we can also go over the, like, extremity, but in a reduced manner. Okay, like, this will be considered as the highest one, and this will be your lowest one on this one. Okay, and this is your average here. All right, got it. I hope this is clear. If not, just let me know. Or do you have any questions? Also, let me know. Meanwhile, I'll be drinking some water. Okay. All right. So moving back to our, okay, let's move back to our this day two in, like, notebook. So what you are seeing here right now is the univariate analysis using histogram. And I just explained what exactly your histogram is all about, right? Like, it's a distribution for certain intervals. So showing you, like, the frequency of each interval. So right now what we have here is, like, this facet grid, and this is your data frame here. And u is equals to species, and everything is there, right? SNS dot his plot, right? Like, we've got this certain data here. And now if you notice here, this certain part, is again, like your satosa. And this again, like, we have got here some overlap here again, and we are plotting our petal lengths here. Like, all this value is your petal length, and the frequency we have here is this much. like on the y-axis. Okay, all right. And also we can also do it with the petal width, which I did. And you can see that, for the petal width, the frequent, like the overlap is somewhat smaller. Okay, but Satosa is again totally segregated from its peers, like, Versica and Virginica, and it's quite distinguishable even now with the help of petal, like petal length. And we, scroll down a bit, and you can see it's nothing but a mess, like literally a mess here, right? Like how if we talk about the Satosa here, like, the Satosa here, okay, and like, okay, like it maybe like till this point, like, for Cephal length, till this point, like for 1.12, some value here, or maybe like 1.2, I don't know, like I'm just making a wild guess here, but still it's extremely overlapped, right? Extremely overlapped, so you cannot make any, like good decisions after it, like about this certain graph. But the much worse is this one. Like literally, it's all Setosa, versicle, and Virginica is totally a mess in this one for the sepal width. So I just gave a precedence or an order to my each feature. So I just gave it like, petal width and petal length are doing really good. But whereas sepal length and sepal width, like they are totally a disaster. Totally a disaster. All right. Okay. So, all right, so that was your univariate analysis, but with the help of histograms. All right. And now let's talk about the univariate analysis, but with the help of PDF, which we just saw. Okay, so like I'm just creating some random like values here. So how exactly you can have those though? So you just need to pass this KDE as true and line width, like, the line width will be the line width of this PDF here. Okay, and you can also see like I am literally I'm using histogram here, and I will gonna like, like this is for the kernel density estimation. So it's basically, like checks for the central tendency. Okay, checks for the central tendency. All right. Okay. So you can see like there is an overlap between versicolor and virginica, whereas setosa is again easily distinguishable. All right. So now, like we have got this here. Okay, this is again overlapped. All right, and yeah. Okay, but like what we care about here is this about this, like this graph here, this graph. Okay, and now what else we have here? SNS dot, like your hist plot is there, and we are basically doing this. Petal width and hue is equals to species, and KD is equals to true. So again, we have got this like histogram again. Okay, like you can see, like I'm just making those graphs again, and the value is almost similar. All right, so that was your univariate analysis, but with the help of PDF. Now let's talk about CDF. Okay, what exactly is your CDF? And it will be your cumulative distribution function. Okay, so it will be like what exactly your accumulation firstly, like, when you need to perform accumulation sum, how exactly it will gonna work? Array 1, 2, 3, and 4. This is your array. And when I perform, like cumulative sum of array will be like 1, 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4. So what exactly am I doing here? I'm taking my present value and I'm adding that value to my previous value as well. All previous values actually. So certainly one doesn't have any previous values here, but two does. So therefore, like we actually added 1 to 2, then we added 3 to 1 to 2, and then like 4 to 1 to 3. So you can see like we got here 1, 3, 6, and 10. So these will be my cumulative values here in terms of summation. Okay, all right. That's okay, I guess. And now it is your like histogram is this. Okay, so your hist and bins is np dot histogram and df petal length, and I'm just taking those values here. Okay, and I'm printing out my histogram and sum of it. So firstly, I would like you to tell you like what exactly your cumulative distribution function is all about. Okay. So CDF or cumulative distribution function. Okay. So it's the area under the curve of PDF. Honestly, मैं भी बताता हूँ कैसे exactly. Let me tell you how exactly it is. So in PDF, like sorry, in AUC or area under the curve, how exactly we calculate area under the curve? Certainly with an lower bound with a not n but with a lower bound and upper bound, right? So what exactly we have here as lower bound, like it will be your LB and it will be your UB. Okay, so let's talk about this. So I will be just representing my LB to UB of my PDF function. All right. So if I give my CDF as how exactly I can give it. So like let's say A to B, like my lower bound will be A and upper bound will be B for fx and dx. And your f of x in this case, your f of x in this case is what? Like your probability density function. All right. Okay. Uh, all right. So let's see, like, what do I mean by this? So let's say, if I, make this as a, like, as a plain English statement, how exactly I can do it. So CDF tells you tells you about the, about the random variable, random variable, no, tells you about the mm, uh, chosen random variable with a probability, with a probability. Let's see how. Let's exactly see how. So if I plot out PDF and CDF, like let's say if I plot out PDF and CDF, how exactly it will gonna look like. Let's see. So we've got this here. Okay. And your CDF will be on, like you can like literally have your CDF on either of those axes, but I am actually going with the, like on the Y axis here. So your CDF will gonna vary from sorry, 0 to 1 only. Okay. And let me just plot this out here. Okay. Let's say like, like this is your CDF and which cannot exceed 1 at any cost. And your PDF is here this much like this. Okay, like this is your X and this is your, sorry, this is your PDF and this is your CDF. Okay, and this is your CDF here and this is your PDF here. All right. And now for this one, like let's say this is for 0.5, this is for 0.8, and this is for zero point 0.2. Like I'm just making a wild guess here. What do I mean by this? And like let's say we have got here, like a few values here, 1, 2, 3, 4, 5, 6, 7, 8, till whatever the value it can actually get to. Okay. So now let me actually drop a perpendicular from this point and to this point. Okay, like for 5. What do I mean by that? So if I drop a perpendicular from this very point, Okay. So for this one, like what exactly my coordinates will be. So it will be 5, comma, and if I go here vertically, it will be 5, comma, 0.85, right? Okay. So now let's talk about this. So if I P1, like I'm just calling it P1. Okay. So P1 is given as 5, comma, 0.85. And this 5 is your, like PDF value, a random variable value from a Gaussian distribution. Okay. And this is your CDF value. Okay. And now what exactly we need here? So what exactly we care about here about this certain region? Okay. About this certain region. How exactly, like what exactly this region will be telling us here? Okay. So till this point, like this is for 5. So what I can say here as in plain English, like 85% of my like PDF values, or like like sorry, this is your PDF, or I can just simply write here as X. 85% of my like X values will gonna will gonna like less than be will be gonna less than will be going to less than like 5. 85% of X values will be going to less than 5. Okay, so how exactly I can write it? So like if I have this, like this straight line on my x-axis, or somewhere around here, I will be having this 85%. Or this on this 85%, the 5 will be sitting on top of it, and all values which actually comes before it will gonna have a lesser value. Like definitely we're just gonna have like values lesser than this. So your PDF and CDF also gives you the information about the percentiles. PDF and CDF gives you info about the percentiles as well. Okay, so that powerful this PDF and CDF is. So is that clear? Like I know I couldn't complete on the mathematical formulations here, but I do have some time constraints here. So therefore, like I just went with the intuitive approach. But if you do have any questions about PDF and CDF, then please ask. Otherwise, I can actually wait for like 1 or 2 minutes. If not, just I can just go, like I can just continue rest of the lecture. If you do have any questions, then please ask. Do you guys have any questions? Any questions? Okay, I'm gonna take that as a yes. Like you don't have any questions, so now I'm resuming my topic here. Okay, all right. So that was your like smooth version. So how exactly I can like show you like you can plot CDF. So it's quite easy. Just go with the, again, you need to calculate the histogram here. So I'm then calculating the PDF, the smooth version of histogram, and the integration or cumulative of all PDF values. So you can just use this with np.consum, right? And there you go. You've got this beautiful looking graph. And if I interpret some information from this graph, how exactly I can do it? Let's see. So for this one, so for this one, like for this one here, like let's say for this one, for this one, 5.5. Okay. And we've got here this one. Okay. For this one, we have around 0.82, and we have got here 5.5. And now 82% of my data will be we're gonna exceed 5.5 centimeter in petal length, centimeters, of course. So that's how you can read it. Like we just discussed how exactly you can read PDF and CDF plots. Okay. All right. So moving on, if we go back here, so you can see like these are your bin values, and also I just plotted out each like I just iterated over each of my species here, like like Setosa, versicolor, and virginica, and I dropped this species column because I do not need that species column here to have it as like PDF versus CDF graph, because it's basically categorical data and we can only plot PDF and CDF on a numerical data here. All right. And when we do that, got this again like good looking graph, and there you go. Like and and in the end, what exactly am I doing here? I am just for petal length as versicolor. So I'm just extracting all petal length and petal width and sepal length and sepal width from my data here. Okay, sorry, for the only for the petal length here. So only for the petal length, I'm extracting Setosa, versicolor, and virginica differently. So now, if you notice here as well, like in this certain portion here, like this Setosa graph, this Setosa is what like it's totally isolated. Okay, and for this one, and for this one, what we have here, like again, we have got some overlap here. All right, okay. So, like you can make again those uh, observations again. All right, so now we will gonna see the effect of mean variance and standard deviation on like with the help of outliers. So let's say like I again extracted, but I just segregated Satosa, virginica, and versicolor differently on on each of their data frames, and I've got this mean value here. Okay, so like let's say if I write here the concept here, like the outlier, not like just the outlier effect, like on mean variance and median. Let's see like how exactly it's gonna vary, especially for the mean and median. Let's actually only talk about like mean and median here. So for this one, let's say we've got this array here, and this array contains a few values: 3, 4, 5, and 6, and 7. Okay, and if I see this on my x-axis, and if I calculate its mean, how exactly I can do it? So it will be 3 plus 4 plus 5 plus 6 plus 7 divided by 5. So how much it will be? It will be 12, 6, 18, 7, 25. It will be 5. So the mean of it will be 5 here. Let's actually introduce an outlier. Instead of having 7, let's add like 100 here. So array underscore 100 with an outlier, of course. So 3, 4, 5, 6, and 100. So this value will be what? 3 plus 4 plus 5 plus 6 plus 100 divided by 5 again. Okay, so it will be how much again? So like 7, 5, 12, 6, 18, 118, right? This much, I guess. I hope my calculation is right. Yeah, 118 divided by 5. Okay, so it will be how much? 23 point, I guess, like 23.6, right? This much this value will be. Okay, and now, okay, so now you can see, like, like there was a drastic shift when we introduced an outlier in our data set. Okay, so what exactly you can conclude from here? Your mean gets shifted, like whenever with an outlier, always. Okay, that was your mean effect on the outlier. What about the median though? So let's say we've got this array here, and we have here 1, 2, 3, 4, and 5. And if I calculate the median of this array, how much it will be? 3. Because what we do basically to calculate median, we need to perform certain steps. First, rearrange all values in an ascending order. Second, like pick the middle one. All right. So if I take this array here, so we have already rearranged them like in an ascending order, and the middle one is this. If we have even values, so we basically take the two middle values and take the like average of it, basically plus summing up and dividing it by 2. That is why I just don't want to get into the I think like even number here. But what if we have array again with an outlier introduced in it, like we have here array with 100, 1, 2, 3, 4, and 100. So it doesn't matter. Like even if I perform this, like let's say if I do 1, 2, 100, 3, and 5. If I do this, I would again have to rearrange all my like values. So it will be 1, 2, 3, like 5 and 100. So again, my middle value will be what? 3. So my median, like doesn't get affected by outlier. All right. Okay. So now you can, like I just performed the very similar calculations here. So mean value with an outlier and without an outlier is this much. And we have got this here standard deviation and like 0.17 and everything is there. And median with an outlier without an outlier are remains the same. And there you go. So we ended our second notebook as well. So last but not the least, we have the third one here. Not like this though, not one this one. Okay, not this one though. So now we'll be talking about some interquartile ranges and like it will be a piece of cake, believe me. But do we have any questions so far? Let me actually test. Like let me actually check. Do we have any questions? Everything's clear to everyone? No. Okay. So let's talk about this. So again, I'm reading out some data here and like segregating my data from versicle and version because like it's the similar thing. So what exactly your percentile and quantiles is? So quantiles are nothing but when you like we already discussed what your percentiles values are all about, right? But your quantiles are when we segment the data frame, or sorry, data set across 0 to 255 to 55 to 50, 50 to 75, and 75 to 100, like in 4 segments here. So like you can see the minimum value we have here is this much, which we, okay. And like this is your 25th percentile. Okay, you can see like, I'm just calculating NP dot percentile here, Setosa, and the range I'm taking here is as 0 to 100, and I'm taking the gap as 250, 25 here. So it will be 0 to 250, 250 to, like 25 to 50, sorry, 0 to 25, and 25 to 50, and 50 to 75. Okay, so this is what we have here. And now, right. mm, okay, all right, and you can see 50% of my pattern length of Setosa flower will going to have length of less than 1.5. Okay, and like it's the similar observation which we just made. Like it's, I'm just familiarizing you with some new terminologies, but the concept remains same here across all like whenever you actually encounter this percentile terminology anywhere in the data analytics. Okay, so I'm also calculating here 99 percentile as well. So for the Setosa, we have 1.9. For versicolor, we have 5.051. And for Virginica, we have this 6.802. So 99% of my data for Setosa in terms of petal length will be like less than this much and this much and this much. And your interquartile ranges. So let's also talk about this as well. So I told you like this for this one. Okay. So this is your interquartile range, like the very first one here. Okay. And this is your quarter one, like an IQR. So how exactly you can calculate the IQR? IQR is nothing but the difference between your Q3 and Q1, quarter three and quarter one. So quarter three is nothing but your 75th percentile value, and quarter one is nothing but your 25th percentile value. So you can literally calculate this IQR by having these values. So it is not a big deal again. Okay, so you can have like it, but your IQR is good for outlier detection, right? Like it is basically used for IQ, not most of the times, okay, but not the best metric though. Okay, like we can actually use kurtosis instead of using IQR. All right. So again, we go back here, and we have like median absolute deviation. We also have it here, and we've got this period or series array dot mad, and we've got this median absolute deviation. Okay, and petal length dot values, again values, and yeah. So median absolute deviation will be what? Like how much your median is, like deviating from its uh, by like let me actually show you like from each point basically. So if I have like let's say I have got this x here, and this x contains several values x1, x2, and x3, and xn, and I take median of x. Okay, and it will be your mx, let's call it mx, right? So your median absolute deviation MAD will be given as x1 minus mx ka modulus, right? So this is like why exactly we are calling it absolute, because we only care about the like the quantity, not the result, not the sign, like if whether it is positive or negative, but the result in the end. Okay, so like how much it is actually deviating from, like how much each point is deviating from its median. Okay, and now so this is your median absolute deviation. Next we have here is box plots. So basically these box plots are based on your interquartile ranges. So when we talk about this here, like let's say for this one, okay, and here, like let's say for this one here, and for here as well, and for here as well. Okay, and so for this one and for this one, okay. So this is again, you can see like this certain, like like this, like I don't know like if you can see this or not, but this median point, this point, like it is actually looking some of your IQR data points which we just saw, like sorry, IQR plot which we just saw. So this middle point is your 50th percentile, and this one is your 25th, and this one is your 75th. All right. Okay. And again, like you can make the same observation, but this is somewhere actually like where you can actually determine what exactly the overlap between Satosa and versicolor. So can anyone in the chat can tell me like what exactly the overlap between Satosa and versicolor here, like based on this one, given that like this is 25th, 75th, sorry, 50th and 75th, this value. Okay, and this is zeros, and it will be 25th, 50th and 75th. Okay, so can anyone tell me here, like, like my question is here, you like overlap percentage between versicolor and Virginica. What exactly it will be? Anyone? I'm waiting for your responses here. No one? Okay. Let's talk about this, how much it will be. So when we talk about like it will be 0 and it will be 25. So if you talk about this certain range and this certain range, this certain like portion is overlapping with one another. Okay, 0 to 50 to 25. Okay. So what we can say here, 25%, 25% of my versicolor and Virginica is overlapping. That's it. Okay. All right. And same with the violin plot. And your violin plot will be like it will be a concoction of two different plots. The first one will be your, let me first bring it up here. It is your normal plot or your distribution plot in this case. Okay, this is your distribution plot. Okay, and in this case, this is your box plot. All right. Okay. Uh, okay, and like you can see, like we have already talked about these two plots again. Okay, so we don't really have to now. And again, like like this will be your 50th percentile value, this will be your 25th and 75th. All right, and these will be your whiskers. Like these are called whiskers, right? And when we go back here, so all right. Last but not the least, we have got here, like this last plot here. We have this. This is called KDE plot. Okay, so KDE plot will be you can actually read it as its central tendency, like what the as you actually go away from the central tendency, the fewer data points you actually get. So when we talk about this here, like for this to this, we have got most points between 4 to 4.5. Like for what? For versicolor, for versicolor. And also for this central tendency, like whatever the value we have here, 1.12 or something. Okay, we have got the most points here, and the lesser point will be here, here, and here. So that is how this KDE actually works here. Okay, so it is a concept called contour. So like you can actually consider this as like you have got an you know, like an egg here, like this is your egg, right? And you basically slice this egg across many like segments, and whatever the spherical shape would actually like emerges from each slice. Like let's say from this, the spherical shape somewhat like will gonna look like this, and for this it will gonna look like this, and this, and like like we've got only three segments here, so only three, and each shape will gonna like expand one another. So we just like squash it down on the one another, like it will just gonna look like this. Okay, so this is your contour. Okay, and your contour, like like the most points actually has at its like at its center. So this is where the most points are at. Okay, right? Okay, so all right, so that's like let's actually not focus upon this because this is totally a different thing. Okay, and like I just summarized the plot here from all analysis we can see. You can like where we have. I'm just gonna like put this notebook again here. So yeah, this is it, guys. So if you have any questions, then please ask. I'm ready to answer those. Yeah, that 25% was right. Yeah, 25% is right. If you have got this in at once, so definitely it is right. Any questions? Anyone here? We can actually take an AMA for like maybe for 5 to 10 minutes. Okay, if you have any questions, then please riddle me with those questions. Or quiz me as much as you can. Any questions, guys? I'm actually reading your questions here. Okay, so tell me. No questions? Huh? No. Okay. Then thank you so much for joining in, guys. It was like lovely talking to you, or maybe lovely teaching to you here. Okay, and I always love or always enjoy teaching. It's the best way to like enhance your knowledge as well. It's a win-win situation, I guess, for me and for you both. All right, and yeah, thank you so much for joining in again, and I wish you good night, or good day, or good evening, and whatever the time zones you are in right now currently. And yeah, just rock and see you then. Okay, bye bye. Take care.